and the damping force or the viscous force also acts in the opposite direction. The viscous force is proportional to the velocity. So mass times acceleration is equal to the sum of forces acting on the system, which is going to be Ft, which acts towards the positive direction, minus Kx minus C dx dt. This can be rearranged and written as m second derivative of x with respect to time, which is acceleration. So this is mass times acceleration plus C dx dt plus Kx equals to Ft. Now I will divide all the terms by m, and this equation can be written as the second derivative of x with respect to time plus c over m dx dt plus k over m x equals to 1 over m ft. So our goal is to solve this second order differential equation so that we know how the position of the mass changes with respect to time. So in order to do this, we will assume that the solution is of the form a e to the power lambda t. So this is the general form of the solution, and now we can also obtain the general form of dx dt and the second derivative of x with respect to time. So dx dt is a lambda e lambda t, and the second derivative is a lambda square e lambda t. Let's substitute them in the differential equation. So now the differential equation can be written as a lambda square e lambda t plus c over m, a lambda e lambda t plus k over m, a e lambda t. Now I will assume that the forcing function is equal to 0. So either I can say that I will assume the forcing function is equal to 0, or I can say that I will obtain the homogeneous solution. So this partial differential equation has two types of solutions: homogeneous solution and particular solution. You will obtain particular solution if you keep ft on the right hand side, but if you assume it is equal to 0, you will obtain the homogeneous solution, and the homogeneous solution will also satisfy this differential equation. So for simplicity, we will only obtain the homogeneous solution, which is the reason I have kept 0 on the right hand side. Now here you may notice that a times e to the power lambda t is common in all terms. So we will get rid of it, and we obtain lambda square plus c over m lambda plus k over m equals to 0. Now this is a quadratic equation, and you know the solution of the quadratic equation. So in this case, there will be two solutions because it's a second order equation, and the two solutions are minus c over m plus minus square root of c over m square minus 4 times k over m divided by 2. I will transfer 2 to the numerator, and I can write c over 2m plus minus square root of c over 2m square minus k over m. So there are two solutions of lambda. Lambda is also known as the eigenvalue of the system. So there are two eigenvalues of this system. So if we now remind ourselves of the solution of x, then we can write it by making substitution for lambda. So the solution to this differential equation is equal to c1 e to the power lambda 1t plus c2 e to the power lambda 2t. So this is the solution, and c1 and c2 will be determined by the initial conditions. Now there are three scenarios created by this lambda. Let's discuss those three scenarios, because the behavior of x with respect to time is going to be different in those three scenarios.